Dear students, in today's class we are going to discuss two important topics, area vector and the electric flux. These two topics are very important because understanding of these two topics will make a ground for understanding Gauss law and its applications. Gauss law is one of the very important topic of this chapter. Let us start with the discussion of area vector. Area vector, you know that area is a scalar quantity. The information which you have already with you, according to you, area is a scalar quantity. If you have a square of side A and I ask you what will be the area, you will say the area will be product of the sides. So it will be A square. But in some problems, it is necessary to treat area as a vector. We have discussed the case of square. So let us take a square which we have placed in xy plane. I cap represents the unit vector along x-axis. J cap represents the unit vector along y-axis. K cap represents the unit vector along z-axis. So this side is a vector and it will be written as a j cap. And this side is a vector, it is along x-axis, it will be written as a magnitude into unit vector along x-axis, that is I cap, it will be written as a I cap, right? So area vector will be product of the sides. A square can be taken common. Inside you are left with I cap into j cap. It will give you the k cap because product of I into j will be k. We know this thing already from the vectors chapter which you did during your +1 class. Then xy plane, in xy plane you have placed your square. Direction of your area vector is along the z direction, means normal to that plane, normal to the xy plane is representing the direction of the area vector. Square is a very simple example, but when you practically deal with the things, you will have curved surfaces, such as you can have a cylindrical surface. The surface of cylinder is curved. It doesn't have straight walls. These are curved one. You can have sphere. The surface of sphere is also curved. So in that case, we need to divide the given enclosed area into large number of very small area elements. That you can see in the figure. We have chosen a cylinder. We have drawn many lines in this cylinder. The purpose of these lines is to divide the cylinder into small area elements. This is the first area element, then this is the second, this is the third area element, fourth, fifth and sixth. This way, we have divided the curved surface into small area elements, and all these area elements will be considered as individual planes. So look, this is the first surface S1 which is considered as a planar, and this is the unit vector, or you can say this is the normal which is perpendicular to this area element. Then S2 is the another area element. This is the normal to the surface. This is the normal to the S3 and S4, S5, so on. We have drawn several area elements and the perpendicular to those area elements which will represent the direction of area vector. So there is a convention that if you are associating a vector with area element of a closed surface, it is taken in the outward direction. So if you have a cylinder and this particular is your area element, then there are two options. You can draw the area vector in the outward direction, and as per the second option, you can draw it inward. But the convention is there, you will always take the area vector in the outward direction. So these are two different shapes in which we have calculated the area vector. Area vector will be magnitude of the area, that is delta S, multiplied with n cap. N cap is the unit vector which is perpendicular to the area. So in that case, this is the area delta S, n cap is perpendicular to it. So the area vector will be delta S vector, the vector sign is there, which is product of magnitude and direction. The magnitude is delta S and the direction is n cap, and n cap is perpendicular to delta S. Similarly, if you have any arbitrary shape, for the curved shape, we know that we need to divide those provided areas into small area elements, right? So this is the one area element which we have chosen, and n cap is the unit vector along the normal. Then delta S vector will be given as n cap into delta S. Now the next topic is electric flux. Electric flux over an area in an electric field means you will talk about the electric flux when you have placed any area inside the electric field is the measure of the number of electric field lines crossing this area, right? Let us understand this figure. These gray lines are representing the electric field lines. Delta S is the area which you have placed inside the electric field. Then the electric flux is the measure of number of electric field lines crossing this area. If you look from 1 to 7, all these electric field lines are crossing the area delta S. Area delta S intercepts 7 field lines. So electric flux is the number of electric field lines crossing the area element delta S will give you the electric flux. E is the magnitude of the electric field. Delta S is the area element. Now, if you tilt the electric field with respect to area element, in this case, if I draw n cap here, the unit vector perpendicular to the area element, in that case, the electric field E and the unit vector n cap having angle of 0 degree between them, right? Now, if I tilt the electric field such that the electric field makes an angle theta with this normal, then what will happen? The number of electric field lines crossing the area delta S will be smaller, because if you look there, the field line which is number 1 and the field line which is number 7 are not intercepting the area delta S. They have crossed away from the delta S. So only 5 lines are intercepting the area delta S, starting from number 2 to 6, 1, 2, 3, 4, 5. Only 5 lines are crossing the area element delta S, right? So if the number of lines has reduced, and we have defined on the previous page that the number of lines has direct connection with the electric flux. If the number of lines has reduced, it means that due to tilt in the electric field, the electric flux has reduced. Next is the symbolic representation for the electric flux. Electric flux is represented with the symbol phi. We write E at the bottom to show that it is electric flux, because in the coming chapters you will be studying magnetic flux too. So to distinguish, we write phi E, right? This delta symbol means the change in the electric flux. Delta is to show the change in the electric flux. Phi is the symbol for flux. The bottom E means the electric flux. So delta phi E is the electric flux, and delta phi E is given as E vector dot delta S vector, right? This delta S vector is the area vector, which is the first topic of this video, right? Then we know that scalar product of A vector and B vector will be AB cos theta, and A vector cross B vector, the cross product will be AB sin theta. We will be using this thing. If you choose your A vector as E vector and B vector as delta S vector, so you can write AB cos theta means E delta S cos theta. So this way you can write it, right? The angle theta is here. This angle theta shows the orientation of electric field lines and the area element. With this, the several cases will appear. Case 1. when electric field is normal to the area element. So we can see in the figure, this is our area element and we have chosen electric field normal to the area element. During this situation, the angle between area vector and the field line will be equal to 0 degree, because we know that area vector is normal to the area element and we have chosen electric field normal to the area element. So both electric field and area vector will be parallel to each other, by which the angle will be equal to 0 degree, and cos 0 degree is equal to 1. When you make these substitutions in the expression of electric flux, then it gives you E delta S, which is the maximum electric flux. In second case, when electric field is along the area element, means this is our area element and electric field is along it. Due to this situation, the angle between the area vector and the electric field is equal to 90 degree. Theta is equal to 90 degree means cos 90 degree in the expression of electric flux, and cos 90 degree is equal to 0. So delta phi will automatically become equal to 0. Electric flux is 0 when you orient your electric field line and the area element parallel to each other. Now the case third, if you have angle theta greater than 90 degree, right, means your area vector is aligned in the electric field in such a manner that your angle theta is coming greater than 90 degree, right? So 0 to 90 case was easy. Now the angle is greater than 90 degree. Then we consider the quadrants. We know that the first quadrant is from 0 to 90 degree. The second is from 90 degree to 180 degree. The third quadrant is from 180 degree to 270 degree. And the fourth one is from 270 to 360 degree, right? You are given with theta greater than 90 degree. Theta greater than 90 degree means you are in any of these three quadrants, right? You can be in the second quadrant, you can be in the third quadrant, and you can be in the fourth quadrant. By using the trigonometric relations, we know that in the first quadrant all are positive. In the second quadrant, only sine and cosecant are positive. In the third quadrant, tan and cot are positive. And in the fourth quadrant, cos and sec are positive, right? So for theta greater than 90 degree, E delta S cos theta, electric flux is going to be negative. Delta phi will be negative. That I have written after school to college. This is the way to remind. The first letter in the first quadrant is after and the word is A, means all positive. In the second quadrant, school S. S means sine and cosec positive. In the third quadrant, tan and cot T are positive. And in the fourth quadrant, college C, cos and sec are positive. If the angle is less than 90 degree, it means that you will be in the first quadrant. It means cos theta is positive. It means delta phi is positive. The electric flux is positive. Now, to calculate the electric flux through any given surface, we need to divide the surface into small area elements, right? We have done this thing that to calculate the electric flux, you will divide the area into small area elements. So the total electric flux phi E will be given as summation E vector dot delta S vector. This summation is for the sum of all individual area elements, right? Then if you take your area element to be extremely small, then summation will change into integral. If you choose your delta S to be very small, then it will be E vector dot ds vector. Delta S has been shifted to ds. ds represents the small change, right? So it will be E ds cos of theta by using A vector dot B vector is equal to A magnitude, B magnitude and cos of theta. So it will be E ds cos theta. Now this circle has some meaning. Simply you represent integration like this. While representing the electric flux, you are putting a circle sign on it. This circle sign has meaning. The circle on the integral indicates that the surface of integration is a closed surface. Means you are doing the integration for a closed surface. It's not an open surface, it's a closed surface. So the final expression is phi e is equal to integral over the closed surface E ds cos of theta. This is the expression for electric flux. Now let us discuss two important points regarding the electric flux which will help you to solve the objective questions. The first thing, phi e is equal to E dot ds. Means phi has direct dependence on E as well as ds. It means that if you will increase the electric field, your phi E will increase. Secondly, if you will increase the area element, then your electric field is also going to increase. To understand this thing, we have written two lines. Electric flux increases with increase in number of field lines. We have chosen two area elements. This is the first area element S, the same area element S. Means these S and S are same in area. In first case, we have drawn few lines, 4 lines only, and the electric flux corresponding to it is phi A. In the second case, we have increased the electric field. The strength of the electric field is directly dependent upon the number of electric field lines. If you increase the number of electric field lines, it means that you are increasing the electric field, right? So in this case, only 4 lines are here, and in this case, 7 electric field lines are there, right? So if E has increased, phi E will increase. So phi B is greater than phi A, because in case of phi A, the number of electric field lines are less as compared to phi B. Second, the electric flux increases with increase in the size of the area element. We have chosen same number of electric field lines, 1, 2, 3, 4, 5. 5 lines are here and 5 lines are here, right? But in this case, this area element has smaller size as compared to this area element, right? This one is bigger in size, this one is smaller in size, right? So due to the increase in the area, the number of lines which are intercepting the area element has increased. In this case, only 3 lines are crossing the area element, and in this case, all the 5 lines are crossing the area elements. So if you increase the size of the area element, electric flux is going to increase as phi 1 is greater than phi 2. Now this question is very important. Is electric flux a vector quantity? You have written your electric flux as E vector dot delta S vector. E vector, electric field, is a vector. Delta S vector, area vector. You said the area will be a vector, right? Is electric flux also a vector quantity? No. Electric flux is a scalar quantity because phi E is E vector dot delta S vector. Dot means you are taking the scalar product. And when you take scalar product, your answer is also going to be a scalar. That you can try. I give you two vectors. I give you a vector as 3i cap plus 2j cap, and I give you b vector as 2i cap. A vector dot b vector. What will be the answer? Write down in the comment and tell me. First you write the answer and write whether your answer is a vector or a scalar. You will find that your answer is going to be a scalar quantity. So whenever the quantity is derived from the dot product of two vectors, it is going to be a scalar quantity. Then let us calculate the units of electric flux. The units of electric flux can be calculated by knowing the units of electric field and the units of area. Units of area, SI system in meters will be meter square, and units of electric field will be calculated from here, that electric field is force divided by the charge. The SI units for force are Newton, and for the charge these are Coulomb. So it will be Newton per Coulomb. So the net units will be Newton meter square per Coulomb. The next thing is to calculate the dimensional formula for electric flux. Phi is E delta S. E can be written as force upon charge into delta S, right? So force is mass into acceleration. Mass will give you m. Acceleration is velocity per unit time. Velocity is further distance per unit time. So 2 per unit times are going to be there. So it will be LT minus 2, right? Then charge is current into time, because current is rate of change of charge. So charge can be written as current multiplied with time. So it will be ampere into time t. ds is the length into length, so it will give me L square. So you put your force here, you put your charge here, and you put your L square at the space of ds. You will have this expression. You can combine the terms. It will be ml cube a raised to power minus 1 and t raised to power minus 3. This is the dimensional formula for phi e. Thank you so much for watching the video. Kindly share, subscribe and comment the answer which I have asked you. Thank you so much.